Hello everyone, my name is Ankit Agrawal. I'm a research professor in the Department of Electrical and Computer Engineering at Northwestern University. I'd like to thank the organizers for this invitation and the opportunity to present our work here. Today I'll be talking about deep materials informatics, where we look at some illustrative applications of deep learning in materials science. These are our team members and collaborators and the funding agencies that supported the works that I'll be presenting here. So to give you a bit of background about the kind of research I do and our group as a whole, I strongly believe that in this era of big data, there are these two fundamental technologies or subfields of computer science, data mining and high performance computing, that need to come together more than ever before if we are to solve the big data challenges. So in our lab, we routinely take data mining algorithms and scale them up to thousands or tens of thousands of processes so that they can really work on big data efficiently. And then I'm personally also very interested in applying these techniques in different application domains like materials and healthcare and social media and so on. So of course, in this presentation, we'll talk more about materials. Uh, so we became interested in this back in 2011 when the Materials Genome Initiative was announced. And as part of that, we've had the opportunity to work on a lot of exciting projects. For example, right now I am co-leading the artificial intelligence and high-performance data mining tool group at the Center for Hierarchical Materials Design, CHIMAT, which is a $60 million center of excellence sponsored by NIST. And then I was part of our Air Force Mili project, which focused on the microstructure aspect of materials, a DARPA Simplex project on thermoelectric materials. And currently I'm part of this NSF Big Data Spoke, the Midwest Spoke on integrated materials design. This was some internal Northwestern funding for exploring data-driven analytics for steels, based on which we got some external funding from Defense Logistic Agency, where we are now looking at data from Navy hull steels. And then there has been a lot of interest lately from industry. A lot of companies have approached us to try to learn and apply and integrate these techniques into their industrial workflows. And here is one such relationship with Toyota that was formalized a couple of years ago. So this is going to be the outline of this presentation. I'll start with some basic paradigms of science and some deep learning terminology. And then most of the time I expect to spend on illustrative examples of materials informatics in terms of forward and inverse models. And then in the end, if you have time, we'll look at some of the tools that we have developed. So this is one of my pet slides, paradigms of science. If we look at how science and technology has evolved over centuries, not just years or decades, we can very clearly identify these four paradigms of science. So in the very beginning, all science was purely empirical. Everything was based on observations. So today that is famous as the experimental branch of science. In the 17th century, when calculus was invented, we could take real world phenomena and put them as mathematical equations. So the second paradigm of model-based theoretical science became popular, and things like laws of thermodynamics and Newton's laws of motion, they are good examples of the second paradigm in material science. Then when in the 1950s, when computers were invented, we could now solve these equations on computers and on supercomputers. So that's where this third paradigm of simulations or computational science became popular. And density functional theory, molecular dynamics, finite element simulations are some excellent examples of that in materials. Over the last 15, 20 years, so just the sheer volume, velocity, and variety of the data that is being generated by these first three paradigms has far outstripped our capacity to make sense of it. And that's where this fourth paradigm of big data-driven science has become popular, where the goal is to extract insights out of data using data as a resource, in addition to the computation. And needless to say that this is very much like finding needle in a haystack. So it's a very challenging problem. And I like this example very much because not only it signifies the difficulty in finding the right needle, but also the ease or the risk of easily finding the wrong needle. Because if you're not careful, if you just take some data, take some technique, put it together, the technique will churn out some numbers because it is domain agnostic. But if we don't know what we're doing, we can very easily fall into the trap of wrong needles. So that's why it's important to have the necessary, domain expertise, AI expertise on the same table for us to apply these techniques properly. And on our side, the way we have been doing that lately is using deep learning. And as most of you may know, it's a rediscovery of neural networks fueled by the availability of big data and big compute. Um, and it has had a lot of success, a lot of groundbreaking success in a lot of different domains. I'm sure you've heard of its role in game playing and natural language processing and computer vision, self-driving cars. So deep learning is driving basically a lot of modern technologies nowadays. But like any other technology, deep learning has its advantages and challenges. So we already saw that it requires big data and big compute for it to work. Also, architecture search and interpretability are other challenges because there's no optimal way to find the best architecture for a given problem, although there are some guidelines. And then similarly, it's not straightforward to interpret a deep learning model and understand why it is making certain predictions on some data. Although it is possible to interpret it to some degree, it's not as straightforward as traditional algorithms. But typically, the advantages of deep learning outweigh the challenges most of the time. And the biggest advantage of deep learning is that it is feature engineering free. So we no longer need to, manually hand engineer attributes, features from our data before applying machine learning. We can just give the raw data to deep learning, and it can figure out the best features by itself. And then if you have enough data, it can also give us more accurate models, as you can see here. As you increase the amount of training data, you get better, more accurate models. And there is a crossover point after which that happens. Before that, it's deep learning is usually not that accurate, because it needs big data. And we have been able to identify this crossover point for some of our applications that we'll see in a few slides. And then they're also very fast. So it requires big compute to train the model, but once the model is properly trained, it can churn out predictions in a matter of milliseconds or even faster. Deep learning comes in different size and shape and color depending on what you want to do with it and what kind of data you have at hand. So if you have regular tabular numeric data, you can use fully connected networks. If you have image data, you can use convolutional neural networks. Anything to do with time series, like language modeling or weather prediction, any sequential data, you can use recurrent neural networks or its variants. And then generative adversarial networks are a special class of deep learning networks, which are based on generative models. And it has two networks, generator and discriminator, which are trained in a competitive fashion. And when properly trained, the generator can be used to, generate uh, uh, fake realistic data. Or if you've heard of deep fake images and videos, this is the technique behind that. So it's very powerful. It can be used like anything powerful. It can be used for both good and bad. And we have tried to we've been trying to use all these networks and more in material science. So these are some of the works that we have done over the last 8 to 10 years in terms of both in terms of forward models. So forward models are property prediction. So given a material, what's the property? So that's a forward model. And inverse models are given a property, what is the material? So it's an optimization or discovery problem. And then structure characterization is technically an inverse problem, but I've listed it separately because it has some unique challenges because of dealing with image data. So of course we can't go through everything here, but we'll look at a few examples, particularly those that deal with deep learning. So let's begin. The first example I want to show is DFT data mining, deep learning the chemistry of materials from only elemental composition. So I'm sure most of you will know that DFT is a very powerful simulation, which can calculate the properties, many useful properties of a crystalline compound. And over the years, we have used data from a lot of publicly available data sets and built composition-based models and structure-based models. So using, for example, the chemical formula of a compound here, like say ferric oxide, we can calculate a library of attributes, which we call physical attributes, to represent this material, and then that vector can then be used for machine learning. And then similarly, we can use something like Warnow tessellation to capture the local environment around each atom, and then use those quantified measures like bond lengths and so on as the representation. So these are ways to add more and more domain knowledge into the model, which is very much desirable and should be done whenever possible. But as computer scientists, we were also interested in something diametrically opposite. That what if we do not provide any domain knowledge to the model? So what can it do? And because that's where deep learning excels, it can work on raw data. So we developed this model LMNet, which takes only raw elemental fraction as input, which means that, for example, for ferric oxide, it only takes input as the fact that it has 2 atoms of iron and 3 atoms of oxygen. And it doesn't even know what is iron, what is oxygen. It is just columns. There is no valence information, no periodic table information, nothing. And then we found that it can give us more accurate and faster models if we have enough data. And it can also learn the chemistry of materials. So here I'm showing 3 different curves. So this top curve is random forest, which is one of the traditional machine learning algorithm with the elemental fractions as input. And this green curve is again random forest with physical attributes as input. As input. So if we add this kind of domain knowledge, obviously the error goes down significantly. But we find this LMNet, which takes only elemental fractions as input. It can beat both these curves at different points. It can beat the random forest with elemental fractions with just a few hundred training points, and random forest with physical attributes with a couple of thousand training points. So this is the crossover point for LMNet in this case. Um, and further, we also found that even though LMNet did not have any periodic domain expertise or domain knowledge built in, it could somehow figure out that, for example, sodium, potassium, lithium, cesium, and these group one elements, they all belong together. So it was treating them in a similar way, without having any a priori information about that. So it actually learned chemistry by itself to some degree, which is very consistent with other applications and other success stories of deep learning. And here I'm showing one example where the LMNet was able to recover convex cell of a titanium oxygen binary system, which was withheld from the training data. So this is an example of when you have big data, you can use deep learning on raw inputs and get excellent performance. So what is stopping us to make from making these networks deeper? So why not we make them more and more deep to get better performance? Theoretically, they should be more accurate, but they suffer from this vanishing gradient problem, as you see here. So this is a training curve, learning curve of a 17-layer network, which is LMNet, the one that I showed in the previous slide. And if you make it 24 layers, the performance actually goes down. So the error goes up. And 48 layer, the error becomes even more. So that's because of this vanishing gradient issue. And that has to do with the fact, with the way these networks are trained, because the error of the predictions are back propagated with respect to the weights to update the weights. And if these networks are very deep, by the time the gradients reach the beginning of the network, they almost die out. So there's no more training. So residual learning is one of the ways to deal with it, which was introduced a few years ago for image data in the context of convolutional neural networks. And then one of our students adapted it for numerical data, and he came up with this idea of individual residual learning, where he introduced the skip connection after every layer, every fully connected layer, and that helped in significantly enhancing the accuracy. So this top curve here is the 48-layer curve, which is same as this curve. And using this concept of individual residual learning, the error can drop down by almost 65%, as you see here. So this is an example of how you can enable deeper learning when you have big data. So for example, here we have hundreds of thousands of data points, so we can do that. And this was presented last year in KDD, which is the topmost conference of data mining in computer science. So that's what you do when you have big data available. But in material science, unfortunately, there's more often a problem of small data than big data, especially for experiment data. If you want to get the benefits of deep learning, we can use this concept of deep transfer learning, which is actually a very simple but elegant concept. That first we train a model on big data, in this case OQMD, and same LMNet, and then use that trained LMNet model as a starting point to refine the weights of the model when we train on the smaller data set. So that way, instead of training from scratch, you start with a very good guess and then refine it on your particular data set. So when we did that, we found that it can significantly improve the accuracy compared to training from scratch. So this is the smallest data set, experimental data set, and this is the training, the learning curve for training from scratch, which can get the best accuracy of about 0.13 electron volts per atom. And transfer learning can go all the way down to 0.07 electron volts per atom. And interestingly, this accuracy, this final accuracy that we got, is very similar or even slightly better than DFT's own accuracy. Because DFT itself is a simulation, so it has some error with respect to experiment. So by this transfer learning approach, we can get similar or better accuracy in much less time, much less resources, and so on. And this work was published last year in Nature Communications. If you're interested to get more details. So moving from DFT to finite element simulations, this is an example of applying deep learning to learn localization relationships. If you have a two-phase composite like this, white and black voxels, and if you apply a loading condition at the macro scale, how does that get distributed at the micro scale? That is the localization problem in a nutshell. So it is desirable to find these regions of high strain. So because that's where the crack initiation is expected to happen. So finite element modeling is what is typically used for this, and we use 3D CNNs because this is nothing but a 3D image. So when we did that, we found that compared to other data-driven models like MKS, the deep learning model can get us much better accuracy, much closer to the ground truth, which in this case is finite element simulations. And I show here two examples of contrast 10 and contrast 50. And contrast here is basically the relative Young's modulus of the two phases. So if the contrast is high, that is more difficult to analyze and make good predictions on. So we can get up to 3% and 5% error on contrast 10 and 50. And more details in this publication last year from ACTAMAT, if you want to take a look. This example is a recent work in collaboration with NIST and West Virginia University, where we're using deep learning to learn crystal plasticity. So how to identify prior deformation history. So on a typical stress strain curve, if we apply a loading condition and go to this red point, and then we release the load, we'll go back to this this blue point. So it has some prior loading, which has deformed the material. But let's say that's unknown. So now the question is, can we start from this point and then figure out what the prior deformation was? So the way they do that is to apply a small reload and take this material to this green point, which will give us the strain maps. And we believe that these strain maps will should have all the information that we need to identify the prior deformation history. So we got these some strain profiles data from our collaborator from West Virginia University, about 3,000 strain profiles with different sample widths from 2 microns all the way down to 62 nanometers. Different test reload strain and slip types, so 1 slip and 2 slip systems, and then 3 levels of prior deformation. To what degree the prior deformation had occurred. So first we applied some augmentation to this data because it's too small for deep learning. And then we used residual learning, the same idea of skip connection that I mentioned before. And we found that compared to a correlation function based method, which gave 68% accuracy, which is actually not bad, because it's a three class problem. So random guess will only give you 33% accuracy. So this correlation based method baseline that we're using is 68%, which is quite good. But the deep learning model can actually help us to achieve almost up to 92% accuracy. And if we combine the top of one models using ensemble modeling, we can further bump the accuracy to almost 94%, which is significantly better. And then another feature that we found of this model was that we could use this to predict stress strain curves. So here you see the blue curve is the predicted stress strain curve of a test data point, which was not included in the training set, of course. And then this red is the actual stress strain curve for that. So this is a recent word just appeared in scientific reports a couple of months ago. So you can take a look if you are interested. Then I guess this is my last example, industrial materials design. So as I said, we've been working with some industry partners to try to help them to integrate these techniques in their workflows. So this is one example of Toyota. So in this figure, you see this is a typical processing workflow. We have some materials, and it goes through a series of processing steps like rapid cooling, molding, hot deformation, heat treatment, and we can measure the properties at different points. So being experiment data set, although this is very rich and sophisticated workflow, it gives us a lot of interesting and rich data with a lot of challenges because the data is very small, being experimental and noisy and heterogeneous. Because we can have numerical data composition, and we can have image data for structure and so on. So we came up with this combined numerical plus image model workflow where we extract features from this SEM images using the same concept of transfer learning that I described before, using a pre-trained VGG16 network, which is trained on a big image data set. It can extract useful features on this, from this SEM image data. And then we can use something like PCA to reduce the dimensionality of that because it's still quite high dimensional. And then the resulting features can then be concatenated with the numerical features like composition. And that can then serve as a representation of the material. And then we can apply some machine learning techniques on top of it. So when we did that, we found the resulting models to have less than 5% prediction error for the properties of interest, SCG and BR, coercivity and remanence for this magnetic materials. And this has a potentially huge impact because industries do this at a very large scale. So if we can use a model to filter out the not so promising candidates, we can avoid the high-end processing for them and only use the valuable SEM time, SEM man hours for the promising candidates. So it can actually result in a huge cost savings. And then in turn, that can also translate into faster magnet design. We can find the materials with the desired properties faster, as well as the process optimization. We can find the best processing routes to get to that material, get to the target material. So I get more details in this ICDM workshop paper if you're interested. So many of these examples and a lot more, both from our group and elsewhere, are discussed in this prospective article in Informatics Communications AI Special Issue. So please take a look if you are interested. So let's see, I have a couple of minutes, so let me show you quickly quick demo. So we have this website, there are a lot of tools available here in different domains, materials, healthcare, and so on. So for steel, for materials, we have this steel fatigue strength predictor, where you can put a steel of your choice and get predictions of fatigue strength in real time. And same idea with formation energy predictor. So you can put a bunch of compounds, and this element model that I discussed, it can give you predictions of formation energy and can compare them with other models if you want. And the same idea with we have things for thermoelectric properties, Martensite start temperature, and photovoltaic predictors, and so on. So take a look if you are interested. And then I guess I'm going to end with this kind of humorous take on what I feel about this whole thing. That's some people think that AI, machine learning, and big data analytics are is like drinking from a fire hose to quench the thirst, and that's definitely not the case. And this goes back to my earlier example of finding the wrong needles, because there have been numerous examples of AI gone wrong. Because it's very easy to, there are so many pitfalls here that it's easy to misapply them. And so, because especially now, AI and machine learning has become such a hot buzzword that, and apparently it is very easy to learn these techniques and apply. So just this sort of caution that there's no harm in doing that as long as you learn these techniques thoroughly and not just take them off the shelf and just apply without understanding the assumption behind that and so on. Otherwise, we can very easily fall into some things like this. So with that, I'd like to thank you for your attention. And if there are any questions, please feel free to reach out to me on my email here. So thank you so much.